This video is about testing hypotheses about proportions. By the end of this video, you should be able to explain what a hypothesis test is and be able to perform a one proportion z-test using these 5 steps. First, you will state the hypothesis, and later on, not in this chapter, but later on, we'll talk about the alpha level. That'll also be in that first step. You will need to check conditions, state what test is being performed, calculate the p-value, and state the conclusion in context. So let me give you a context. In one plant, and they're kind of molding out of metal these ingots, only about 80% of the ingots have been free of cracks. And when there is a crack, they have to melt it down and recast it, and it's a very expensive process. So they want to reduce the number of ingots that have cracks. So in an attempt to reduce the cracking proportion, the plant engineers and chemists recently tried out some changes in the casting process. Since then, 400 ingots have been cast, and only 17% of them have cracked. Should the management declare victory? Is this enough that these changes have made a big difference? Or is the 17% just due to luck, due to random chance, that it happened to get some of the ones that, more of the ones that didn't crack in that group of 400? Okay, so we are assuming that we can treat the 400, newly cast ingots with the new method as a random sample, which actually isn't a random sample, but let's just treat it as a random sample for now. Okay, and we are wondering is the 17% that we observe merely a result of natural sampling variability, or is it low enough that we have enough evidence to assume that the management and the to assure management and the true cracking rate is now below 20%. Okay, these questions happen all the time, where we say, is this percent this, or has it changed since then? Okay, and in questions like this, it is really good to do a hypothesis test. Okay, in a hypothesis test, we make a hypothesis and then see if we can reject that hypothesis based on our data. Okay, so in this example, we will assume that nothing has changed. Okay, that the proportion of defective ingots is still 20%, and we will ask ourselves, based on this sample of 400, is that enough evidence for us to conclude that this hypothesis is not true? Okay, so we begin by writing a hypothesis that looks like this, and this is H sub 0. Okay, the null hypothesis is what it's called. The initial hypothesis, the null hypothesis, in this case is P is equal to 0.20, that the proportion of defective ingots is 20%, and I also defined what the variable was. It is the proportion of defective ingots. Okay, now we also write a second hypothesis, something called the alternative hypothesis. Okay, and this is what we think would be true if the hypothesis was false. Okay, frequently this is what we're trying to prove is true. We want to show that the proportion of defective ingots has decreased from before. Okay, we want to show that it's decreased, and so we set that as the alternative hypothesis. Okay, what we think would be true if the hypothesis was false. Okay, so it's written H sub A, and the A stands for alternative, and we are assuming that proportion is less than 0.20. Okay, and that'll come into effect as we perform some calculations. Okay, the next thing we do before we can actually do any kinds of calculations, we need to check some assumptions and conditions. Okay, now the two most important, now the conditions do include independence and the large enough sample condition and the other conditions, but the two most important ones are randomization. Okay, explain why we can assume that it's random. Okay, so we are assuming that the 400 ingots are the same as a random sample. Okay, the other really important condition is the success failure condition. you calculate n times p and n times q. Okay, so n, in this case, the sample is size 400, and p, the hypothesized p-value, is 0.2. Okay, this value is 0.2, not 0.17. Okay, and it's important that this is different from a confidence interval. In a confidence interval, your n times p and your n times q for the success failure condition come from your p hat, from your sample. Okay, in a hypothesis test, we are assuming that p is a certain value, and we are doing all of our calculations assuming that that hypothesized p-value is the true p-value. Okay, so this is different from a confidence interval. Okay, so we expect to see in this casting of 400, 80 that are defective and 320 that are free from cracks. Okay, so we need to check, I should have written this in here, that both are bigger than or equal to 10. Okay, and both are, I'll say, larger than 10. Okay, because these conditions are satisfied, we can do our hypothesis test. And the name of this hypothesis test, which I'll give you later, is a one proportion z-test. Okay, so as we do the hypothesis test and do some calculations, we first need the standard deviation. Okay, and we're still using the equation from a sampling distribution, which is the square root of pq over n. Okay, but this time for p and for q, we are again using the hypothesized p and q values. That's why there's p sub 0 and q sub 0, because these are from the null hypothesis. Okay, I will again point out that this is different from a confidence interval. In a confidence interval, we use p hat and q hat from the sample, but in a hypothesis test, I'm assuming that the p-value is the hypothesized p-value, and all calculations are done using that hypothesized p-value. Okay, so once we have our standard deviation, we can then plug it in and find a z-score. Okay, again, the z is equal to x minus mu over sigma, where x comes from the sample. So it actually, in this case, a better way to write it would be p hat from the sample minus p sub 0 from the null hypothesis divided by the standard deviation, which depends on p naught, or p sub 0. So using this formula, we get a z-score of negative 1.5. Okay, and what we're asking ourselves is, how likely is it that I would find a sample with a z-score of negative 1.5, given that the null hypothesis is true? Okay. Also, keep in mind that we're looking for this z-score or less based on the alternative hypothesis. Okay. The alternative hypothesis, remember, was p is less than 0.2. Okay. This less than is important. Okay, so we're looking for it being less than this z-score. Okay, so if you wanted to actually calculate the p-value using norm CDF, you could plug in norm CDF from the left bound would be negative 9999, just some really small number, and the right bound would be negative 1.5. Okay, or if you'd rather use values instead of calculating the z-score, you could do norm CDF negative 9999, some small number. The left bound would be 0.17. The right bound is, the left bound is negative 9999. The right bound is 0.17. The mean is 0.20, and the standard deviation is 0.02. Either way, you should get a probability of 0.067. Okay, this value is called the p-value. Okay, which is a really important word. It should be bolded, but it's not. The p-value. Okay, the p-value is the probability of seeing data like the ones we saw, given that the null hypothesis is true. Okay, so Next, we need to make a decision. Okay? If something occurred that has a probability of 0.067% chance of happening, would that surprise us? Okay? If so, then we would assume, or conclude, I should say, that the null hypothesis is false. If that's not surprising to us, then we would fail to reject the null hypothesis. We would be unable to reject the null hypothesis. Okay, and I'm not going to decide here whether that's true or false, but you will need to begin to get used to deciding if that's true or false. Okay, now the final step in the hypothesis test is to give a conclusion in context. Okay, now I'm going to show you both ways of doing it, whether or not you reject the null hypothesis. Okay, so if you think that something happening that has a 0.067 chance of happening, you would reject the null hypothesis and you would say this. With a p-value of 0.067, I reject the null hypothesis. There's enough evidence to conclude that whatever it is in context. So in this case, it is the true cracking rate is below 20%. Okay? If you decide to not reject the null hypothesis, meaning that you're not surprised by something occurring that has a 0.067 chance of happening, then you would fail to reject using this phrase. With a p-value of 0.067, I fail to reject the null hypothesis. There is not enough evidence to conclude that blank. In this case, it is the true cracking rate is below 20%. Okay. Later on, we will decide before we do the hypothesis test at what p-value we will accept or fail. This is bad. We will reject or fail to reject the null hypothesis. Okay. Let me point out the fact that the reason I cross this out is because you never accept the null hypothesis. Okay. You can either reject it or fail to reject it. We can't prove the null hypothesis true. We can only fail to reject it. Okay. This value, this kind of boundary value at which we either reject or fail to reject the null hypothesis is called the alpha level. And we'll talk about that in a future chapter, because there's more to that idea than just setting the boundary value. Okay, the name of this kind of hypothesis test, because we'll study several kinds of hypothesis test, is called a one proportion z-test, because we're working only with one proportion, and we are using the normal model, which is related to z-scores. Okay, and here is the purple box from the textbook. The conditions for the one proportion z-test are the same as for a one proportion z interval. Okay, and we test the hypothesis, and here's the null hypothesis, using the z statistic, which is this, and the standard deviation is from this formula. Okay, so there's some important facts in that table. Oops. Okay, other alternative hypothesis. In this example, we tested to see if the proportion was lower than it was before. Okay, if it's lower than the hypothesized p-value. Hypothesized proportion. We can also test to see if the proportion is higher than it was before. Okay, in this case, it wouldn't make sense, but in other cases, you want to see if it has risen higher than it was before. Okay, which you just would switch which side of that p-hat value you're testing. Okay, or we can test to see if it's different from before. Okay, either higher or lower. We don't care. We just want to see if it's different than it was before. This is called a two-sided alternative. Okay, because you're testing it could be higher or lower. Okay, the important step is if it's a two-sided alternative hypothesis. When you get done calculating your p-value, you will have to multiply by 2 because you're dealing with both tails. Okay, and I will state, by the way, that a one-sided alternative hypothesis that is higher than would look like this, which probably is not surprising to you. P is some hypothesized value, like 0.2 for this example. Okay, and the alternative for the different from would look like this. H sub A is P is not equal to 0.2 or whatever the hypothesized proportion is. Okay, so in summary, here is the 5 steps of a hypothesis test. You first state the null and alternative hypotheses. Okay, later you will also state the alpha level, but that's for a future chapter. You will next check the conditions. The 2 most important conditions to check are randomization, stating exactly why you can assume that this is a random sample, and checking the success-failure condition by plugging numbers in and making sure n times p and n times q are both bigger than or equal to 10. You next state the test you're doing. This is a 1 proportion z-test. You must state that name. And fourth, you do the mechanics where you calculate the p-value and you state that p-value. And then number 5, you state the conclusion in context. You either you reject or you fail to reject the null hypothesis and give that in context. Okay, so this video was about hypothesis tests for proportions. Thank you so much for watching.